Hello everybody and welcome to lesson 9D. I can solve problems using properties and theorems about central and inscribed angles. So please recall that a central angle is an angle with its vertex at the center of a circle. In the diagram to the right, angle ACB is a central angle with a 120 degree measure. So also recall that arc length is a linear or curved ruler measurement. It's really a fraction of the circumference. Well, today we're going to talk about arc measure. Arc measure is the amount of curvature of an arc measured in degrees, and it is not the same thing as arc length. So if I'm looking at arc AB, it has an arc measure of 120 degrees, and its arc length would be 1/3 of the circumference, whatever the circumference would be. So keep in mind that measure and arc length are not the same thing. So in the above diagram, the measure of arc AB would be 120 degrees. And we know its arc measure, but not its arc length because we don't have the radius. So we have three types of arcs. Our first is a minor arc. And a minor arc has a measure between 0 and 180 degrees. Okay? Here, arc DF is between 0 and 180 degrees. We designate minor arcs with just two letters with the arc over it. The second type of arc we have is actually a semicircle. And semicircles have arc measures of exactly 180 degrees, and we designate them with three letters, this time GJI, where it's basically it's the arc as you trace along those three letters, and the endpoints of that arc are a diameter. And our third type of arc is a major arc. And major arcs measure between 180 degrees and 360 degrees. And so we also list them as three letters with the arc over them. So KNM is a major arc because it is larger than 180 degrees. Notice that's very different to arc KM, which would be a minor arc. The measure of a minor arc is equal to the measure of its central angle, whereas the measure of a major arc is 360 degrees minus the measure of its central angle. So if I want the measure of arc AB in this picture, it's strictly 70 degrees, whereas arc ACB is 360 minus 70 degrees, which is 290 degrees, because it's that reflex angle that goes everywhere but the 70 degrees. Congruent arcs are arcs with equal measure that lie in the same or congruent circles. So keep in mind, to be a congruent arc, you also have to be on a circle with the same radius. So let's do some examples. So if I want to find the measure of arc AB, the measure of arc AB is pretty easy. It's just the strict 65 degrees. So that means from here to here would be 65 degrees. It's the same as the central angle. And the measure of angle BOC would be the same thing as the measure of its arc. Well, BC is intercepted by angle BOC. So if this is 90, this would also be 90. And the measure of arc CDA, well, C to D to A is everything except, so I'm going to trace that. CDA is here. It's everything except the 60 degree angle and the 90 degree angle. So it'd be 360 degrees minus 65, not 60, 65, minus 65 minus 90, which gets me a total of 205 degrees. And then let me do this in purple. The measure of arc CAB, well, I'm going from C around to A and then to B. That's everything except the 90 degree angle in that circle. So it'd be 360 minus 90, which is 270 degrees. Let's look over here. In this example, I want to find first the measure of arc DE. And when you look at this picture, we have all of the arcs in the circle except DE. So in order to find DE, I just have to take 360 degrees and subtract off all the other arcs, the 122, the 55, the 120, and the 42. And when I do that, I get that the measure of DE is in fact 21 degrees. So from here to here is 21 degrees. And if I want to find ACD, well, that's going from A to C to D. That's those three arcs added together. So the measure of ACD is going to equal 55 plus 120 plus 42. So the measure of ACD is in fact 217. All right, moving right along. We had some of these problems at the very beginning of the year, but it's been a while. So now I want to find what is the minor arc formed by the hour hand, between the hour hand and the minute hand at 2 o'clock and at 10:30. Well, first let's set this up. At 2 o'clock, my minute hand is pointing straight up at the 12, and my hour hand is pointing at the 2. Now, if you recall, there are 12 segments on this circle. There are like 12 sections, and 360 divided by 12 is really 30 degrees, which means that each of these segments here is really 30 degrees. So if I'm going between 12 and 2, the measure of the arc between the two hands would just be 60 degrees. Now at 10:30, it's a little bit harder. My minute hand is no longer pointing straight up the 12, it's actually pointing straight down at the 6. And my hour hand is not at 10, it's halfway between 10 and 11. Right? Because the hour hand keeps moving. So when I'm thinking about these segments, I'm breaking this back up, I've got several of them here. These guys are all 30, but this is, because we're at the half hour, this is halfway between 10 and 11, so it must be 30 divided by 2 or 15 degrees for that segment. So I've got 1, 2, 3, 4 times 30 is 120, plus another 15 degrees, to get me a total of 135 degrees. All right, let's now learn about inscribed angles. An inscribed angle is an angle whose vertex is on a circle and whose sides intersect the circle. In the figure below, this figure down here, BCA is an inscribed angle, and it's not supposed to be BC, it should be BA, because it's the arc at BA is its intercepted arc. So this arc right here is its intercepted arc. And the inscribed angle theorem actually states that the measure of an inscribed angle is exactly half the measure of its intercepted arc. So that means that the measure of angle BCA is going to be half the measure of arc BA. So using the diagram above, if I want to find ACB, and I know that ACB is 10 minus x, right? Or x minus 10. That has to be equal to half of arc AB, which is x plus 20. So to solve this, I'm going to multiply both sides by 2 to kill that fraction, right? So I end up getting 2x minus 20 equals x plus 20. I'm going to subtract the x over. I'm going to add that 20 over, so I get x equals 40. And when I plug back in, this would be 40 minus 10, which is 30, and this would be 40 plus 20, which is 60. 30 is half of 60, so I did it right. Okay, here's a corollary though. If two inscribed angles of a circle intercept the same arc, then the angles are in fact congruent. So the measure of angle 1 would be half of arc AB, right? Because they're both intercepting this arc here, AB. And the measure of angle 2 is also half of arc AB. Therefore, angle 1 would be congruent to angle 2. So let's take a look at this. This is a little bit different. It's actually not dealing with the arcs, but we'll take a look. In the circle below, F is not the center of my circle. I know that CF is 1, and FA is 8, and EF is X, and EB, FB is 2X. Now, if I draw in two segments here and here, what I actually end up doing is creating a pair of similar triangles, because if you notice, these angles here are congruent, and we're splitting up our triangle into two similar triangles. So I could actually solve this by proportion. I could say that my smaller triangle, x over 1, is equal to my larger triangle, 8 over 2x. And I could cross multiply to solve this. I'd get 2x squared is equal to 8, divide by 2 to get x squared equals 4. So x is in fact 2. And that's how I would solve that problem, by similar triangles. Okay, moving right along. There's another corollary to this theorem. It says that an angle that is inscribed in a circle is a right angle if and only if its intercepted arc is a semicircle. Well, this makes sense. If we look at this, if AB is a diameter, that means the measure from here to here must be 180 degrees. Right? That arc there is 180 degrees. Well, C is an inscribed angle that is intercepting that arc, so it must be half of 180, which is in fact 90 degrees. So the measure of angle ACB must be half of 180, which is 90 degrees. In the inscribed triangle to the right, AC is 4, CB is 6. I want to find the radius. That's from here to here. What I'm going to do instead is I'm going to treat this like a right triangle, because it is a right triangle, and find AB, which I'm going to call X. So I can say 4 squared plus 6 squared equals X squared, or 16 plus 36 equals X squared, which gets me 52 equals X squared. When I take the square root of 52, 52 is the same thing as the square root of 2 times 2 times 13. A pair of 2's can break out, so I get 2 root 13 is X. Well, that's the measure from here to here. This is 2 root 13. So the measure from here to here is also, what did I just do? I'm sorry, guys. Whatever I just said, ignore that. The whole thing is 2 root 13. This is 2 root 13. I just want the radius, so I need to do 2 root 13 and divide it by 2. So I get that my radius is just equal to the square root of 13. That's my answer. All right, let's take a look at this one. Another corollary, last corollary. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So we can inscribe a quadrilateral in a circle if and only if the opposite angles are supplementary. And there's a reason for that. If I look at the measure of angle 1 in this picture, angle 1 is intercepting an arc that is xy. So that's really equal to 1/2 of x plus y. And then the measure of angle 3, which is its opposite angle, right here, it's intercepting the arc z plus w. 1/2 w plus z. So when I think about adding angle 1 and angle 2 together, measure of angle 1 plus the measure of angle 3, that's equal to 1/2 of x plus y plus 1/2 of w plus z, which means measure of angle 1 plus the measure of angle 3. I can factor out the 1/2 since they both have one. I'm left with x plus y plus w plus z. And we know that all of the arcs in a circle must add up to 360. So that's really half of 360 degrees, which means my opposite angles, angle 1 and angle 3, must add up to 180 at the end of the day. So let's do an example. Quadrilateral EFGH is inscribed in a circle. All right, guys, I cannot draw. So what I'm going to do is I am instead going to use some clip art. You guys are welcome to do this too. And when we're inscribed in a circle, oh my gosh, I did it. That's very exciting. We kind of look like this, right? And I need to label my vertices. So I have E, F, G, H, always label in a circle, right? I want to find the measure of angle H, given that the measure of angle E is x plus 20. The measure of angle F is x minus 5. The measure of angle G is 2x plus 10. So I'm going to start off by finding E and G, right? Because they're opposite each other. So I know that the measure of angle E plus the measure of angle G must equal 180. So when I plug that in, I get x plus 20 plus 2x plus 10 equals 180, or 3x plus 30 equals 180. 3x equals 150, so x is in fact 50 degrees, which means that now I know that the measure of angle F plus the measure of angle H must add to 180 as well. Remember, I'm trying to find H. So I plug in. F was x minus 5. I don't know the measure of angle H. And we just found that x is in fact 50. So I have 50 minus 5 plus the measure of angle H equals 180. So this is 45 plus the measure of angle H equals 180. So my measure of angle H in fact equals 135 degrees. That's my answer. All right, guys, that's the end of the notes. Please be sure to take a look at the MML and ask us any questions if you have them. Thanks.